Good evening, everyone. Thank you so much for joining us tonight. My name is Kate Bruns, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Cabot Science Library, I am very, very pleased to welcome you to our program tonight with Graham Farmelo, discussing his latest book, The Universe Speaks in Numbers: How Modern Math Reveals Nature's Deepest Secrets. In just a moment, I'm going to turn this over to Jacob Barandes, who will be in conversation with Dr. Farmelo tonight. Jacob is the Director of Graduate Studies for Harvard Faculty of Arts and Sciences, Division of Science, the Co-Director of Graduate Studies in the Department of Physics, and a lecturer on physics here at Harvard. Now, for those of you who have not attended our lectures before, this Science Book Talk series features talks throughout the academic year by the authors of recently published books on a wide variety of science-related topics. Now, this is our last talk in the series before our summer hiatus, but do stay tuned. We have some very exciting events coming up in the fall that we are just about to announce. And to learn more about the Science Book Talk series or to learn about the bookstore's other upcoming events, you can visit us online at harvard.com and sign up for our weekly email newsletter. Harvard Bookstore's author talks do continue throughout the summer, so please feel free to grab one of our yellow June events flyers on your way out the door this evening. Tonight's talk is going to be followed by some time for your questions, after which we will have a book signing and refreshments in the Cabot Science Library outside this room and across the Science Center entryway. So now I will turn things over to Jacob Barandes, who will introduce tonight's program.
Can everyone hear me? Yes, good. Great. So thank you so much, Kate. Just as a reminder, this is the last event of the Harvard Science Center Presents series. Last but definitely not least, I'm very excited to be here talking with Dr. Farmelo. So this event will feature a conversation between me and Dr. Farmelo about his book, The Universe Speaks in Numbers: How Modern Math Reveals Nature's Deepest Secrets. Before we start, I wanted to say a few words of introduction about Graham Farmelo, our main guest today. So Dr. Farmelo is an award-winning science writer and biographer based in London. He's a fellow at Churchill College and is currently the director's visitor at the Institute for Advanced Study in Princeton. Dr. Farmelo completed his doctorate in theoretical physics at the University of Liverpool and was subsequently a lecturer in physics at the Open University. He chaired the team that produced the Science Foundation course and conceived its interdisciplinary science course, Science Matters. His work in that capacity brought science education into the lives of over 100,000 people. Dr. Farmelo was the editor of the 2003 book, It Must Be Beautiful: Great Equations of Modern Science. He went on to write Churchill's Bomb: How the United States Overtook Britain in the First Nuclear Arms Race, and also a personal favorite of mine, The Strangest Man, The Hidden Life of Paul Dirac, Mystic of the Atom, which you should all seriously go out and buy right after the lecture. It's one of my favorite books about a person whose contributions to physics are absolutely extraordinary, and also to the world. So aside from his marvelous books, Dr. Farmelo has contributed frequently to the press in the UK, Europe, North America, as a regular guest on BBC television and radio. He's also won a number of awards for his work. For his biography of Paul Dirac, he won the Physics World Book of the Year Award, the Costa Prize for Biography, and the Los Angeles Times Science Writing Prize. More recently, Dr. Farmelo was appointed an honorary fellow of the British Science Association, and he won the Kelvin Prize and medal from the Institute of Physics for outstanding contributions to the public understanding of physics. We're all very appreciative that Dr. Farmelo has taken the time to talk with us all today. With that, should we get started?
Yeah, why not?
Great. So, yeah, I have my questions, some of my questions on my phone. Hopefully the battery doesn't run out. So before I get started, I have a very serious question to ask you about your book, about the title of your book. So your book is called The Universe Speaks in Numbers: How Modern Math Reveals Nature's Deepest Secrets. Did you have any difficulty with maths versus math in the UK to the American titles of the book?
No.
Okay.
That's the way Dirac would have answered that question.
Right.
Yeah.
Yes. So there's a joke about Dirac. What is he had one word every hour, right?
That's right, yeah.
That's right.
Dirac, yeah.
Okay. So more seriously about the content of your book, if I may, I'd like to ask next if you could summarize the main thesis of your book.
Yes, I will, but if you'll allow me, I know it's a new political tradition in America and Britain to dodge the question, so let me do that first of all, and say straight away, I'll ignore what you say, and say thank you, ladies and gentlemen, for coming tonight. It's a wonderful thing to be here at Harvard, fantastic university, famous for physics and mathematics. Great pleasure as well to be in America, rather, or I should say, not Great Britain, where Brexit is a complete national fiasco. But I would like to thank you all for sending your negotiator-in-chief just to sorting it out. I can go home a happy man. Anyway, what was your question? No, I do remember your question. Yeah, right, seriously. My contention is that the universe speaks to us in stereo. It speaks to us classically, the way that everyone recognizes, through observation, through the observations and measurements that experimenters make. It also speaks to us through mathematics. Now, I'd like to unpack that, if I may, Jacob, by going back to the most famous person who's ever lived in the town where I'm currently living, Princeton, Albert Einstein. And in 1952, 3 years before he died, Einstein, thinking deeply, as he always did, about what he was doing as a theoretical physicist, somebody thinking about understanding the basic laws of nature. And he wrote to his old college friend that he thought there was one central miracle. He used that word, not something you often hear scientists use, a miracle or eternal mystery, and that is the fundamental ordering at the heart of the universe. Right? It's not just a chaotic mishmash, so to speak. There is a deep order that is not necessarily something that one takes for granted. It is that order that enables physicists to understand the world. Now, I want crudely to divide physicists, if I may, into theorists and experimenters. I know it's not the most perfect of categorizations, but experimenters make their observations. They do their detailed measurements, and you could say, if you weren't interested, well, what's the point of all this? Just making these measurements. Well, what physicists ultimately are seeking to do is to understand how those measurements relate to each other. In other words, to understand that ordering in the universe. Now, a secondary miracle, if you listen to the great physicist Frank Yang, a term he used, is that ordering among these measurements that physicists study, and you get Nobel Prizes if you come up with a sufficiently novel one, is related to the patterns that are studied by mathematicians. G.H. Hardy, great mathematician, said in his mathematical apology for mathematicians, that the central purpose of mathematicians is to understand these patterns of ideas, these eternal patterns of ideas that are made plain by research mathematicians. And he said those patterns were always beautiful, they were completely enduring. Now, most of the time, again, forgive the breadth of the generalization, physicists can go their own sweet way and do their experiments on nature and look for these relationships I've been talking about. And mathematicians can ply their trade in a darkened room, right, with a completely different agenda, looking for these patterns I'm speaking in a way that you will understand, but basically that is what they are doing. Now, the miracle, according to Frank Yang, is that those patterns that the mathematicians are studying, right at the forefront of mathematics very often, or some of them, not all of them, but some of them, are directly relevant to what patterns the physicists are discovering. So what we have is, when you have something like Einstein discovering a new theory of gravity, is he is connecting these these quantities that you can measure or related to those quantities that you can measure, and using advanced mathematics to actually make those connections. And once you've made those connections, you really are in quite a tight straitjacket because it constrains your future theories. So I hope I've made clear that those two things are important. If you didn't have that mathematical dimension to things, then we'd be back in the pre-Enlightenment days, pre-Newton, where you could have a narrative philosophy of nature, for example, the one that Descartes put forward, right, where you did not have this mathematical tradition.
So there's something special about physics, as opposed to some of the other sciences, that it seems to be particularly connected with mathematics.
It is. Again, I must be careful. I mustn't be too rude, at least not intentionally, to other disciplines, because there are great mathematical biologists. Yeah. There are very fine mathematical economists as well. But there is but since Newton, on the 5th of July 1687, published his Mathematical Principles of Natural Philosophy, he really set the agenda. It wasn't just him, incidentally. He was standing on the shoulders of people like Galileo and Kepler, and particularly Descartes, right? But he actually set the agenda. If you go read that preface to that book, that the aim of natural philosophers, remember, he wasn't a physicist, right? He didn't regard himself as a physicist. He regarded himself as a natural philosopher, somebody who makes a rational study of God's creation. Very important, that part about God. Very, very important. Let me plug somebody else's book. Priest of Nature by Rob Iliff, masterpiece in my view, published last year. And that book really, really made it clear, right, through the most wonderful scholarship, that Newton was, more than anything else, a man of God. Everything else was secondary to that. So he was studying God's creation, and he believed, and he set out that philosophy at the beginning of his mathematical principles of natural philosophy, that the job was to understand God's creation in a way that consisted of laws that you set out mathematically, right? And he did that brilliantly, absolutely brilliantly in that book, by actually a law that is incredibly simple mathematically. I mean, you don't even need to be at high school to understand the mathematical law of the gravitational force between 2 point masses. You simply multiply the masses and you divide by the square of the distance between them. And that law is something that holds to an extremely high degree of accuracy right across the universe. That's a fantastic pattern, so to speak, between forces, masses, and distances. And he set that thing out and demonstrated brilliantly, using his mathematics, actually it was geometrical mathematics he used there, that how powerful it was to understand the trajectories of the motion of the moon, trajectories of satellites, of the tides, and what have you. And it also, very, very important thing from Newton, because remember, he wasn't just a fantastic mathematician, he was a fantastic natural philosopher in two ways, as an experimenter and as a thinker about nature. It's quite extraordinary talent. I don't think we've ever seen anything like it. And he was urged on us something that is absolutely fundamental, which is that you set out those things mathematically because they give you the generality and specificity of your theory. There's no waffly words here. And you compare the predictions of those theories, as we now call them, to the most accurate data that you have. Now, that's something we all pretty well take for granted, at least you're in politics, right? You take your theory and you put your head on the block and you compare it to, I repeated myself, but it's so important, to the most accurate data that you have. And if it's wrong and consistently demonstrated to be wrong, you know you're on the wrong track.
So you've been interested in, I mean, from your book, the relationship between mathematics and describing nature for a long time. You say early in the book that as a child, and this is quoting you, it amazed me that a few simple principles underpinned by mathematics we'd only recently learned could be used to predict accurately everything from the paths of golf balls to the trajectories of planets.
Yeah, that's true.
Could you say a little more about those early experiences and how they shaped your feeling about?
Yeah, I'm still in contact with my teacher. I think he'll be very angry with me, but I think it's quite common. When you're at school, you start off when you study science, and you talk about things in a narrative way. That's quite understandable. But as you go on, as you work through your the syllabus, you start basically to define symbols and use formulae, just as we've been talking about here. Now, nobody ever commented on that. The fact that you're importing mathematics that you were doing in a mathematics class, and it works in the natural world. And I still remember, it's right up there with my top 3 or 4 epiphanies in science. This is little old me, this is not everyone else, right? That using an incredibly simple Newton's law of motion, which you can just write on the end of your finger, and you can, by just acknowledging the fact there is a simple gravitational force vertically downwards, and you can actually predict the trajectories of a tennis ball, for example, when it's thrown in space, no matter what angle it is. And you can work out what the longest flight time is, the maximum reach, and what have you, right? Now, maybe this doesn't turn everyone on here, but I thought this was amazing that you could do this. Such simple principles, really pretty simple mathematics, and you could do so much. Now, I loved to do that because that was my first applied maths, study applied maths. But that's pretty much what you're doing throughout your career, taking simple principles, setting them out in mathematical terms, and then making predictions, so to speak, that you can in principle test. And I don't think people make enough of that. That's my point. And it still stayed with me, that fascination.
So mathematics can be sometimes a little intimidating.
A little.
More than a little intimidating.
You might say terrifying for some people.
Terrifying for some people, mystifying for other people, exhilarating for still other people.
Indeed, if you're really good at it, yeah.
Well, yeah. So you find a way to talk in the book about many of the intricacies and many of the intuitions around mathematics, but you do it in a way that doesn't overwhelm or inundate the reader.
Yeah.
How did you navigate that balance between trying to get across, what some of this important mathematics is trying to express?
Okay.
In some cases, you're talking about higher dimensional spaces. You're talking about infinite dimensional groups.
Go on, you'll frighten everybody here, but anyway.
But somehow you managed to do it in a way that is.
You are quite right.
Right. How did you steer that delicate balance?
Well, first of all, I had a wish, a strong wish to try, so far as I was capable, of laying bare what I think is a great intellectual adventure of how you apply mathematics to the real world. Now, as you've eloquently said in your frightening introduction there, right, that if you look at that, if you just go and look online at those mathematics people use, right, it is quite terrifying. And frankly, it may be that someone far more capable than I am will one day be able to explain to a person off the street what a differential manifold is.
Seiberg-Witten theory.
Seiberg-Witten theory, right? And good luck to them, right? I haven't seen that so far. I'm not saying it can't be done. Never say never, right? But what I did think was at least worth a shot was to give a sense of the people who are doing these theories, what they're trying to achieve, a sense of the broad shape of the subject, what people are trying to achieve, the success they had. But to me, and certainly to my publishers who wouldn't have published the book if I'd actually set the mathematics out in detail, it wouldn't have been a practical proposition to describe those things in detail. But I do hope, I don't know, it's for my readers to judge, that they have some sense of how these worlds come together.
Yeah. And sometimes to a humorous effect, you talk about a story. This is somewhat later in your book when you're talking about, a period of time when the connection between mathematics and physics is really sort of flowering again. And there's this anecdote you bring up about a PhD student at her exam, and she's asked by one of her committee members who's a little bit suspicious about this, intensity of mathematics. He asks her what he's hoping is a very clear experimental question: what is the mass of the electron? And you actually put a formula there. She writes M subscript E. As the answer. Yes. So you do give yourself license occasionally.
That does illustrate a point. If I may tell this story backwards, it does illustrate this thing that does frustrate. We're getting into territory in the book here, which is actually perfectly legitimate. People who aren't in physics and mathematics need to know this, right? There are people who think that physicists could take this mathematical approach much too far, and that graduate student thought that, you know, the mass of the electron is something you write down ME, right? While having absolutely no sense, right, of what it is compared with the mass of a proton or the mass of the Earth or what have you, right? They just really don't care that much, right? And that is a problem for actually some very, very good physicists whom I know. Steve Weinberg of this parish recently, he although a great hero of mine, a fantastic, but he thinks there is a great danger that people can fall in love with this mathematics so much that they lose sight of what they're trying to do. And what is that? Is what Einstein told us. It's trying to understand the basic laws of nature, the ordering at the heart of the universe. So it can be taken too far. Right? Now, that's not to say, I'm certainly not writing the whole project off, but I'm just saying that you always have to bear in mind, if you call yourself a physicist, what you're actually trying to achieve.
So I apologize for jumping into the latter part of the book, but I want to
problem.
talk a little bit about the first half of the book. So the first half of the book is really an extraordinary history of, you know, ideas in mathematics and physics that are relevant to what you're doing, but they're also, you know, pivotal developments in the history of human thought. Tell me a little bit about, all of us a little bit about, you know, why you chose to devote a significant part of the first part of the book to that historical, you know, side of your argument.
Okay. Well, in short, I believe that the work that's being done at the frontiers of theoretical physics, incorporating a lot of modern math, is in a direct line, so to speak, to the work of, I go back to Newton. Of course, I'm not so foolish as to think it all started on that summer Saturday when he published that book, but it's a very good place to start. I think most people would accept that, right? Yeah. So to repeat, what I give in the book are what you might call greatest hits, or some of the highlights of that adventure that went from Newton doing his brilliant work of a mathematical theory of gravity and motion, right through to people now who are looking at the collisions between subnuclear particles called gluons, right, and studying those basically two elementary particles, no shape or size, colliding with each other, and finding that to understand them, you have to use mathematics that is smack bang in the territory of what some of the world's best pure mathematicians do. Now, that's what I wanted to do. I wanted to show that these people are not just doing it for the sake of it, right? But there's been a steady development of this mathematical through the ages. Would you like me to give one example or two? Or?
Please, please do.
Okay.
Yeah.
Well, I won't go through them all, but we've mentioned Newton. I think he's had his few minutes in the sun, which he deserved to do in this talk. But another favourite of mine and many other people in this field is James Clerk Maxwell. Now, James Clerk Maxwell was a Scottish gentleman. He also saw himself as a natural philosopher. His favourite reading was the Bible, poetry, Shakespeare, right? And he was had the most supreme intuition about the workings of nature, and he was also a talented mathematician. Right? It's silly to quantify these things. He wasn't quite at the Newton level, very few people are, but he was a very, very good mathematician, and they sent him to Cambridge to hone his mathematical skills because he was a little bit dodgy compared with his fantastic intuition. And straight out of his degree, he was sitting in Trinity College, and he said he was going to attack electricity. And what he meant by that is that there was a huge body of information from experimenters and observers that studied electricity and its relationship to magnetism. This was a craze in the century before. People would, you see these down at your great Museum of Science here, these incredible demonstrations that show the effect of electricity and magnetism, your hair, if you've got some hair, standing up, standing out, and all these wonderful phenomena that you see in museums. These were big, big things in Europe at the time. They were also, this is important, those subjects were the bellwether of quantification. Now that's a fancy way of saying the study of electricity and magnetism that we all use today, right, is it was something that was studied in great, unprecedented detail by people we now call physicists. So they had great, accurate experiments on these things, but they did not have a mathematical theory. And what James Clerk Maxwell, blameless individual, one of my favorite people ever to walk the corridors of physics, what he did was to do something extremely bold. Because how old was he then? He was, in his 20s. He jumped into this field where many of the best, we now call them physicists, in the world were working, and he said, I'm going to have a crack at finding this mathematical theory. And he did that. He did that in the next 15 years or so. He came out with a theory of electromagnetism that the late Richard Feynman, one of the great physicists of the 20th century, said that in the theory of in the 20th century, that will be seen as perhaps the highlight of the 19th century in terms of, not just for physicists, right, but for our everyday life. Just look at how much we rely on electricity and magnetism now. And the
radio waves, television waves, I mean, the internet, yeah.
The lot.
Right.
Right. Now, even Maxwell didn't foresee the internet, but he did lay down those equations. Now, there's something important here that I want to stress this. He did a type of what of natural philosophy that was, I think, extremely enlightened. He was a very, very good mathematician, but the first thing he decided to do in entering this quest to find that mathematical theory was to read up on the experiments of the great experimental philosopher Michael Faraday, who, on the record, James Clerk Maxwell said was his hero. Now, Faraday was not a great mathematician. He was a fantastic experimenter, one of the very best who's ever lived. And he worked in the basement of the Royal Institution, doing experiments, a lot of them on chemistry, some of them in what we now call physics. He hated the word physics, incidentally, right? And he produced a wealth of information, right, and had the most, as I said, amazing intuition about this interdependence of electricity and magnetism. The central thing that Faraday did was he was the first person really to identify the concept of the field. Now, everyone here, if you're an adult, talks of magnetic field, gravitational field, electric field. It was
an MRI machine. You're
exactly right. But it was Faraday who first conceived that when you have a magnet in space and you have space, and obviously you have space around it here, that space is not just completely inert. You can actually do things to it. You can fill it with a field, right? Now, people on the continent, and indeed many in Britain, thought this was a crazy idea. Maxwell, this was his central wisdom, thought this was the key to the problem. And if you look at the origin of that mathematical theory, the things that gave him the head start were, first of all, recognizing that Faraday had identified the right concept, the field, right? And the second thing is that he had the mathematics, which he'd learnt at Cambridge, to handle what he sought to do. And what he sought to do was to describe the interaction between electricity, magnetism, and the ether. Right? He believed that there was this stuff that carried light, right? That nobody had actually seen directly, but they assumed was there. So he set out to have a theory of these things, and we produced that theory. One of the great contributions of 20th century science, and it was standing on Maxwell's shoulders that Einstein, in the early 20th century, started to do his great work.
So there's another thread that runs through the book, and you bring it up somewhat early in the book, but it comes back a couple of times. It's this metaphysical debate between Plato and Aristotle and their views about the world. But it plays pretty strongly into these sort of divergent viewpoints about how science should be done, in physics in particular.
Yeah.
Would you mind talking a little bit about that thread that runs from them to debates that are...
Well, one of the things is that we in the West now, I think, certainly if you're not specialists in philosophy, and I'm not, I should say that, but Aristotle, if you judge it by the year, was the most influential thinker about nature in human history. His thinking about nature was dominant for thousands of years, right? It was extremely influential, but for our purposes, what was so important is that Aristotle, he's a very smart guy, was one an incredibly influential thinker, but he was very, very confident that mathematics didn't necessarily have anything to do with the understanding the inner workings of the world. Now, we don't believe that now. Right? But that's what but he was a very smart guy, had this most capacious mind. Newton, when he went to Cambridge as an obviously very bright student. He was taught Aristotelian motion, and it was still holding sway throughout throughout Europe. So this is why the overturning of that Aristotelian perspective by Newton was so powerful and so revolutionary in the history of human thought.
Plato's idea, was this idea that there was that the world was deeply connected to these ethereal ideas, deeply connected ideas in mathematics.
Plato, I mean, Frank Wilczek, the great theoretical physicist, has written very eloquently on this. But he looks quite a modern thinker because he really did think that that mathematics had a much more fundamentally important role in our thinking. So he looks a much more modern thinker than Aristotle. I might say that one of the things that I particularly like about Newton, and there aren't many things I like about him personally, is that he really did see the ancient Greeks as the people that really started it all. And as he got older, he looked with more and more admiration on the way that the Greeks, right way back to Archimedes and what have you, used mathematics in their understanding of the real world.
Yeah. So you talk in the book, in sort of the historical discussion, about this 19th century Napoleonic standard model.
Yeah.
That in some ways kind of is a predecessor to the standard model we have today. Can you talk a little bit about what
Yeah, I like this because it's a cheeky suggestion by one of my favorite historians, John Heilbrunn. Now lives in England. He's an American historian. I love reading John's work. And he was asked to talk, I forget the exact year, I guess it was in the 80s, might have been early 90s, about the physicist pride and joy, which is a standard model of the forces that are responsible for holding atoms together and understanding atomic structure. What John wanted to do was to show that that term, standard model, that puts a marker down, we physicists have done something great. Physicists had one of these things, right, a standard model, way back at the beginning of the 19th century. And he said that the first standard model of physics, right, was effectively orchestrated by Pierre-Simon Laplace. He's known as the French Newton, especially in France. He was the person who might be said to can reasonably be said to have completed Newton's program. Even the stupendous genius of, I shouldn't use that word, but I will, of Newton, even he couldn't finish off that program of understanding the cosmos because he didn't have sufficient mathematics. But Laplace and a dozen other continental mathematicians finished off that program. What Laplace did was he set up, let me just go back just diverse 1 second. By the time we get to the early 19th century, that is when the subject that we now call physics, right, whether you like it or not, we now call physics, at high school, your pneumatics, your motion, your hydraulics, your light, your electricity and magnetism. It was in the early 19th century when that subject took shape. So that's why we say between friends, but it's really not a bad approximation. They say that physics, as it is understood now, was basically a French invention. Now, from a Brit, that's saying a lot for me to acknowledge that's true. It wasn't. You can't say that of what was going on in Newton's time. Natural philosophy had a much broader scope than that. Now, what Laplace did in his mansion in Arcueil, which is south of Paris, used to be a beautiful site in the countryside, was he set up what is fairly regarded as the first school, so to speak, of mathematical physics. And he believed that everything in physics could be explained ultimately by forces between particles that could be described by simple mathematical laws, very similar to the ones that Newton had set out. And Laplace was a superb mathematician, a superb natural philosopher or physicist. You might call him, perhaps not entirely rightly. And he had this coterie of young physicists around him, whom he encouraged in many ways. All right, by setting up prizes, personal tuition, Sunday afternoon gatherings, to try to bring to fruition this idea that these interparticle forces were responsible for everything. Now, today, with the condescension of posterity, we look at this and we scoff at this. But people were coming from all over, I was going to say the world, but certainly from Europe, right? Were coming to that mansion in Arcoy to see how you did it. And that's why John Harburn said this was the first standard model of physics. Now, as I stress again, it looks very naive now. And what John was doing, tweaking the tale of physicists, was saying that what we regard as the standard understanding of the world, in another couple of centuries' time, people will be saying, oh, these people, they were so crude in their understanding, right? So that's what I wanted to say by that.
I mean, crude isn't the word I'd use to describe it. When I teach some of this introductory mechanics and celestial mechanics, I bring out for my students scanned copies of Laplace's treatise. It's all in French. It's one of the later editions, but I believe he was still, well, maybe he was still alive when it came out, but it's still very true to the original editions. And it is extraordinary, the mathematics that is in there. It looks like an introductory mechanics textbook that we would use today.
Yeah, exactly. That's the point.
And this was from a time when they were using leeches as cutting-edge medicine, right? I mean, right? It's absolutely incredible where physics was at that time.
I know. For a treat, I recommend you get volume 3 of his Celestial Mechanics, a 5-volume completion of Newton's treatment of the cosmos, and look at the beginning, because you see there the most groveling homage to a person you ever see in a physics book, and it's to his buddy Napoleon. Now, Napoleon really did influence the history of electricity. Right? He really did. And he was hobnobbing with natural philosophers, mathematicians, astronomers, and what have you. And he really was interested in those subjects and was a beneficial influence on them. And if you want to see a real brown noser, right, you go and look at Laplace, talking about the greatest beneficiary of of the French, right? In fact, Napoleon even appointed him a minister. I think he lasted for 9 days or something like that. But they were very, very close. And the fall of Laplace and his way of doing physics, which we've been describing, coincided almost exactly with the Battle of Waterloo. The French lost that battle. I forget who was their opponent. When his career was, sorry, cheap shot. When that was over, Laplace's influence did abate, right? And other styles of physics came into play.
So there are a lot of myths about many figures in the history of modern physics.
Yeah, I like to promote them.
Promote, dispel, little of this,
kidding.
little of that. There are a lot of myths about Einstein. We often hear that Einstein wasn't a very good math student in school. That was obviously totally wrong. He was an excellent, fantastic math student. You talk a lot about that in the book. But he was skeptical about abstract higher math once he began doing, special relativity. He began doing his early work in quantum mechanics.
This is key.
Talk, if you wouldn't mind, a little bit about his evolution from someone who, certainly made use of a lot of, what many people would consider advanced mathematics, but his skepticism of the sort of much more abstract, high-level mathematics. Yeah. And his coming around to the realization that this actually was.
This is a central thing, a central point in my book. Even then, there's a little twist to it. History's, what do they say about the truth? It's rarely pure and never simple, or might be the other way around. But that point that you phrased very well, I think, that Einstein was a smart student. There's no getting away. He wasn't a backward child or anything like that. He was a very smart student, right? And extremely curious. I love his the way he cocked a snookered authority. Even when he was an undergraduate, he was skipping maths lectures, he was skipping physics lectures. He thought he knew more than the professors did about the way to study physics. I love the arrogance of that. So I'm sorry to people who are teachers in the audience, but I love that confidence. It may not work for most people, but it's a wonderful thing to.
You have to be Einstein.
You have to be Einstein, so maybe not recommended. Now, there's ample evidence. Right, really ample evidence that Einstein, his friend, wrote this up. Solovine wrote this up in the Letters to Einstein, which is a book which I'd love to read and recommend. Right, that when Einstein was an undergraduate student, he would keep saying, "Look, physics is a down-to-earth subject, and basically what you need is basic mathematics." Now, I'm not by basic mathematics. He didn't just mean the times table, right? I'm not saying it's that elementary, but he's saying that you need. Between friends, the sort of mathematics that Laplace would have used. In other words, that's over 100 years old. You don't need to use the super refined, mind-bending mathematics that the most refined pure mathematicians were using. Now, that's a really important point, because he had the opportunity, when he was in Zurich at ETH, to be taught by Minkowski, and well, in fact, he was taught there for a time, and Minkowski called him a real lazy bones, right? He really didn't want to get involved in that. Now, you have to say, about Einstein, that when he had his great year, 1905, when he came out with a clarification of the energy quantum, the quantum of light, the Brownian motion theory that made atoms and molecules real, and the wonderful special theory of relativity, a modification of Newtonian space and time, you look at those papers and they are maybe, no, I don't think you're stretching a point, they're resolutely unmathematical. Right? Yeah. Now, all right.
They don't involve more mathematics than an undergraduate student studying physics or math would do in their first
and certainly
year
Laplace wouldn't have had any problem at all. That was 100 years ago, right? So you did not see someone flaunting, their mathematical muscles, so to speak. That's probably not a very good metaphor, but anyway, you know what I mean, right? Now, and Einstein believed that. And there's quotes from his letters, which wonderfully are all online. You see him saying, "Oh, you really don't need all this fancy mathematics." But it changed pretty quickly, and it changed when he started to generalize that theory of relativity to a theory that would give us a theory of gravity. This is Einstein often seen as his greatest achievement. I for one, wouldn't quarrel with that. When he set out a radically new understanding of gravity that superseded Newton's. This was an amazing achievement of philosophical thinking, of mathematics, of our thinking about nature. I mean, virtually any serious physicist is in awe of that. And remember what he had to do, right? Just think, he had thousands of pieces of data that supported Newton's theory, and he had to make sure he reproduced all those successes. And then he had a tiny number of pieces of data, like on the perihelion of Mercury, that weren't quite right.
Mercury was going around the sun and sort of spiraling a little bit with every orbit, right?
Yeah, and so he had to explain, and he had to make it consistent with the special theory of relativity, the theory of motion, right? So that's a really tough call. And he found, this is the key point, that he could not do that unless he used what, by his lights and by most people's lights, was advanced mathematics, a mathematics of differential geometry, which had been developed by pure mathematicians like Gauss and Riemann and Christoffel and people like that. And the amazing thing that never left Einstein was that he was going in, and all scientists, particularly physicists, when they go into a really difficult project like that, they don't really know what they're doing. I'm not saying they're ignorant, of course, I'm not insulting them, I'm simply saying they're trying to understand what on earth's going on. You know what I mean by this, right? And he was into this terrain, didn't know what was going on, and then in this bleakness, he found this thing, differential geometry, that was precision engineered to complete that project. It must have looked extraordinary to him, right? It had all been done decades before, and he could then apply those mathematical tools to solve that problem. Now, I love this story, so tell me to shut up if you're going on too long, right?
I teach general relativity, so you can go on.
Your students tell you to shut up. I know. Okay. Anyway, so he's at 1912. He's collaborating with Marcel Grossmann, his old friend, who was the head of the mathematics department.
Who took notes for him in his lectures when he didn't go, right?
Exactly. Yeah. Exactly. And they worked together on a basic theory of gravity and got really quite close to it in 1912. But it wasn't, the pieces didn't quite fit together. And Einstein, again, with commendable honesty, at one point was talking about being like a bewildered ox, trying to understand this mathematics, trying to work out how it fitted with the physics, right? But he was confused, and again, it's no insult to him to say this. It was a really tough problem. Anyway, the summer of 1915, another 3 years later, he's been, again, please don't think I'm insulting him, because we're talking about a truly great thinker here and a great piece of work. He was thrashing around, as I said, like a bewildered ox, his simile. And he did something that he might actually have regretted later on, because he went down to Göttingen, which is one of the great capitals, or was, and to some extent still is, but certainly at that time was, one of the great capitals of mathematics and physics. Just a little line here, because there's a very important thing here. One phrase that they kept using in correspondence, historians show this repeatedly, is they talk about the pre-established harmony between mathematics and physics. Right, a term that can be traced with a bit of with not much imagination to Leibniz, who was one of Newton's bête noirs. But that phrase was Einstein liked that. Somehow they're in harmony, mathematics and physics. Good phrase that. Very popular in Göttingen. He went down there and he gave a talk on his incomplete theory of gravity. Now that's quite a bold thing to do. He knew he was close, but he couldn't finish it off. And in that audience was David Hilbert, who is one of the greatest mathematicians. There were other superb mathematicians in that audience, and Einstein gave, I forget the number, it's 4, 5, 6 lectures. When Einstein left, went back to Berlin, they were talking sotto voce here that this guy, wonderful physicist, but he's really all over the place in mathematics. And again, you can read that in their correspondence. So Einstein goes back to Berlin, and Hilbert is towards the end of his career. And Hilbert was nonpareil as a mathematician, and he saw, who can blame him, an opportunity to actually finish that theory off. Who can blame him? And he rolled his sleeves up, metaphorically speaking, and set to work. And Einstein, a few weeks later, found himself in a real head-to-head fight, intellectual fight with Hilbert. And you can read go home tonight, ladies and gentlemen, and read it. And you can read, they were corresponding to each other.
The melodrama is so thick.
It really is. Thick. Have you noticed? Yes, of course. Yeah, it's a wonderful being. And Einstein, he's only human after all, is obviously, he wants his name on this theory. Who can blame him?
How would you feel if your life's work, if the greatest mathematician in the world got wind of it and said, I think I'll work on that?
He was very close. And you look now at the best, the great work of Jürgen Wren and the other Einstein scholars, and it's clear that Einstein won that race by just a matter of days, in 7 or 8 years, right? Hilbert very nearly got there. There was one formulation, he did beat Einstein.
Right, the action formulation. It's still known as the Einstein-Hilbert formulation.
It is, that's right. It was done independently, so we give them the name. But now, this next bit is critical to understanding Einstein. Einstein believed that it was mathematics that had, in the phrase of someone we're going to come to, Dirac, led him by the hand to that answer. He believed that mathematics had delivered him to the great equations of gravity that he presented, I think it's November the 25th, 1915, right? The people in the audience, probably not many more than are here, saw a new law of nature, right? And Einstein, to repeat myself, thought that it was not data, it was mathematics that led him to it. Now, there's I want to be really clear about this, right? Because I'd be accused otherwise of distorting. The great historians Jürgen Wren and co. have demonstrated that Einstein actually didn't remember that completely correctly, because Einstein left us his notebooks, and you see that he in fact was, even at that stage, going back and forth between a physical argument and a mathematical argument, right? So I'm just being honest about that, but the truth was that Einstein always believed that mathematics, via a natural interpretation of his tensors, would deliver him to that formula. And the reason why that is important is that when Einstein went to his next project, which was a project too far, even for a mind of that greatness, which was to extend the theory of gravity so that it also embraced Maxwell's theory of electromagnetism. So he would have a unified theory of gravity, electricity, and magnetism. Now, the problem is that Einstein didn't have any clear experimental clues that would take him to that theory. So this is where he got his idea, set out in Oxford in a lecture that he gave in June 1933, that what physicists should do, and he called this the method of theoretical physics, not a method, is that they should look at the mathematics in the theory and develop that. Right? not wait for experimental clues, but concentrate on the mathematics. Now, it's important to recognize that that was seen as extremely eccentric. His old friend Wolfgang Pauli basically said, "Oh my goodness, don't let me detain you before that your current theory basically dies. You have become a pure mathematician. You are working with a completely squeezed out lemon, right, of a theory."
In all due respect, Pauli said that about a lot of people.
He did. Yeah. He did.
He's not the nicest person in the history.
No, but he was probably right, actually.
That may be true.
Yeah, I know. And he was a caustic and brilliant critic, but you are quite right. He's not the kind of person you want to go for a drink with. But anyway, I mentioned that because Einstein he was pretty close to ridiculed, right, towards the end of his life, right? Now, today, we think, well, the big mistake that Einstein made was that he ignored the quantum revolution, and it was a revolution. It was more revolutionary than anything else at the time, which was a theory of motion on the atomic scale, which turns out to be really quite different to the motion laws of motion that Newton had used, and Maxwell.
Even Einstein said that relativity was in some ways a continuation
Absolutely
of
right.
that line of thought.
He did not see himself as a revolutionary.
Quantum mechanics was really
that was seriously revolutionary. I mean, if you showed Newton the theory of relativity, someone as bright as that, first of all, he'd be amazed that anyone else has done the work because he didn't do it, right? But the second thing he would say is, well, this is a logical continuation. You look at quantum mechanics, you say, this is loopy. Well, obviously, I don't know what he'd have said, but he would certainly have said, this is seriously, show me why I should believe in it. It really was revolutionary, right? And you're absolutely right to stress that Einstein saw himself, he always refused to call his theory of gravity revolutionary. Right? He really did. Right? He said this is just a development of Newton's law, but that's not true of quantum mechanics. Einstein did not trust that theory, right, and believed that he could build that unified theory without using quantum mechanics. But the thing that interests us for the purposes of our gathering tonight is that Einstein believed that he could develop that theory mathematically, right? And people ridicule that. And I argue in the book that, I hope respectfully, that yes, Einstein was not going to succeed with that theory, right? But that it now looks quite modern in the sense that his belief that you can mine the mathematics of a theory successfully, right? And I do think that is worthwhile. But we'll come on to somebody else who I think was perhaps more forward-looking later on. But Einstein, I do think his thinking was underrated.
So in being mindful of the time, I have two more questions, and then we'll open it up to all of you for questions. There was another lecture that you pay a lot of attention to in the book, and it's a lecture that I recommend that anyone who's interested in physics or in any of this history, or in the future of physics, take some time to read because it's very accessible. It's this Scott lecture by Paul Dirac in 1939. I mean, Dirac is one of these figures in physics who, personally I would regard as the equal to Einstein, but he's certainly much less well known outside of the physics community. Mm-hmm. But this was a really profound set of things he said in this lecture about mathematics.
It is one of my favorites.
If you could talk a little bit about that lecture and what sort of resonance it had.
Oh, with pleasure. I love this, and I agree with you. Go online and look at this lecture.
It's very accessible, very short, and very readable.
Very readable, and there's no hard mathematics in it, so that's, he was successful at doing what you challenged me at the beginning. He really did talk about these subjects in a way that everyone could read. Yeah. So that's my goal, my aspiration to do that. Anyway, Paul Dirac did not discover quantum mechanics alone, right? He came a bit late to the party. It was discovered by Schrödinger and Heisenberg, as Dirac always said, but Dirac was the most mathematically minded of the pioneers of quantum mechanics. Tom Stoppard called him the stick figure of the field. Now, it doesn't mean to say he was made of wood, or it simply means that he basically was a cartoon figure because he wasn't really a vivid character like many of the other people. What Dirac kept doing, right? He kept, in trying to understand the quantum mechanics in its early days, he repeatedly came up against advanced mathematics over and over again, right? So, stop me after a couple of examples. There are plenty more. When he went back to Bristol in 1925 from Cambridge, and his supervisor sent him the first paper on quantum mechanics written by Heisenberg. And Dirac looked at it and said, like many of you would think about many of these papers, nature can't be that complicated, right? Came back 2 weeks later, and he saw that there was one sentence, right? I don't think it's in brackets, but it's a parenthetic remark, that there's something odd in that Heisenberg interpretation of quantum mechanics. And that is that quantities in quantum mechanics, they're not like ordinary numbers. Everyone here who's got even to second grade in math knows that 7 times 8 is the same as 8 times 7, 9 times 11 is the same as 11 times 9. The ordering doesn't matter. In quantum mechanics, you take these central objects known as operators, and the order that you multiply them in does matter. A times B is not the same as B times A. Now that is called, in Dirac's horrible phrase that is now called non-commutation. That is a central theme in 20th century mathematics. And he saw that this thing that Heisenberg, the great mind who first saw this, was not something embarrassing that would just go away, but was absolutely central to the theory. All right? Another one is when Dirac wanted to find a theory of the electron that not only incorporated quantum mechanics, but incorporated the special theory of relativity as well. And he came up with an equation that did that, and it drove him to a mathematical object that we now call the spinor. Now, the spinors were invented in their classical form by pure mathematicians in Germany some decades before, but Dirac was driven to this by trying to understand the electron in terms of physical ideas. Now, what in that lecture you spoke about, called the Scott Lecture, I think it was the 6th of February 1939, just before a few months before the outbreak of the Second World War, Dirac was invited by Max Born, somebody who's a refugee from Nazi Germany, installed up in with a tenured chair up in Edinburgh, and he asked Dirac to do something that you wouldn't ask Dirac to do. A, give a public lecture, because he was a terrible lecturer to the public, and B, talk about...
You can find YouTube videos, by the way. There are YouTube videos of Dirac giving lectures, and he is a terrible lecturer.
Yeah, that's very bad. Thanks for that very bad advice.
Remarkable.
But anyway, yeah, no, you are quite right.
It's remarkable to see.
You are quite right. Yeah. Anyway, the other thing you don't get Dirac to do is talk about philosophy. He was an anti-philosopher, right? Now, I contrast again, right? This is actually quite modern, right? Nowadays, it seems to me that physicists almost queue up to diss philosophy. You try doing that with Newton, he wouldn't know what you meant. You try doing it with Maxwell, he wouldn't know what you meant. You do it with Einstein. I think Einstein was half natural philosopher, half theoretical physicist.
Schrödinger also, yeah, a lot of the...
Yeah. Right. Anyway, so it was a pretty crazy thing to do, but Dirac, he never actually was very explicit about this, but his research was quite thin at the time, he thought. He wanted to rethink his attitude to the way he was doing theoretical physics, applying mathematics to nature. And he wrote this, in my opinion, and I know I'm a bit biased, but I don't think I'm terribly biased, this wonderful lecture on the relation between mathematical physics. And I'll tell you, ladies and gentlemen, the janitor of this building, all right, no offense to janitors, can understand the beginnings of that lecture. It starts with, there is a mathematical quality to nature that is not obvious to the casual observer, which is absolutely true, not often said enough, right? When I started this, having learnt from Dirac, by emphasizing that. What Dirac does is, in words, describe how he thinks you should do theoretical physics. Now, the key thing that is often remembered from that lecture is that it was where Dirac enunciated what he called his principle of mathematical beauty. And that can be stated in words, namely that theoretical physics progresses from one basic theory to the next in ways that are framed in increasing mathematical beauty. So you start with Newton's theory of gravity. You then have a better theory of Einstein's, which is a generalization of that, which has more mathematical beauty. You do the same with classical mechanics, theory of motion, and you have more beauty in Einstein's interpretation. Now, Dirac believed this was something that was a principle across all of physics. And he believed that this was a principle that you could apply, that you had to look for beautiful mathematics and apply it to physics. Now, this seemed extremely eccentric at the time. Let me be really clear about that. Right? There are two phrases that Dirac used in that book, which I love. And I'd give a redundant organ to have coined these phrases, right? One of them, right, and only he could get away with this, but I love it. He says that mathematics is a game in which mathematicians invent the rules. Nobody's walked out? Good, okay. Physicists play a game where nature has the rules, and physicists aim to guess what they are. Right? They're different. He's stressing they are not the same thing.
Right. One is deduction from rules we pick, and the other is induction from experiments to divine what the rules are.
Now, the next statement rams this home, right? And if you don't like the beauty stuff, right? And I have to say on this one, with great respect to Dirac, it's a sitting target for philosophers, that. I mean, how do you define what beauty is, right? Dirac doesn't want to know about that. He just said, I'm talking about mathematical beauty. If you're a mathematician, you know what it means. If you're not a mathematician, goodbye.
He later says that it's one of the things that people across the world would agree on. Like, people across the world would disagree on artistic beauty, but mathematical beauty is universal enough that we would all agree.
That's right. So here's the phrase that doesn't feature that beauty thing that I think is so forward-looking. He says that as time goes on, right, the mathematics that physicists use in their fundamental theories is increasingly the mathematics that mathematicians find interesting. Now, that is exactly the situation that we are in today.
Yeah, I wanted to segue to today also, right?
Right, because you find, as I said when I talked about those gluon studies, right? The most basic thing you could talk about with two fundamental particles with no mass colliding at ultra high energy, one step up from nothingness, basically, and you study those things here, and you find yourself right slap bang in the bailiwick of advanced mathematics. Now, this is extraordinary, right? And this is happening all over now. And this is why, although mathematics and physics, in Freeman Dyson's term, were divorced after the Second World War, they lost interest in each other, they didn't think they needed each other. Now, they've put their differences behind them, and they are working very, very closely with each other. And I think that was very closely foreseen by Dirac, and that's why his lecture has such the late Michael Atiyah, who sadly died in January, he said, this looks like a piece of clairvoyance. That's what he said to me a few months before he died.
I think that's a great a place to segue into asking for questions from all of you. So we have a couple of microphones that are running around, I think. We have one microphone running around. So,
yes, I can get other.
Kate will come around. So we have about, I would say, probably 10, 15 minutes. Does that sound okay? Okay.
This is a great lecture. I think the book is going to be terrific when I get hold of it. How do you deal with string theory?
Right. String theory is, in the words of the great Edward Witten, who is I think the preeminent mathematical physicist of the last 40 years, it is, in his words, the only interesting development of the kind of theory that we use called gauge theory to understand the way atoms work. Now, string theory is a very beautiful theory for experts. It has led to what Atiyah again called a Klondike of new mathematics, and has been fantastically useful for mathematicians. The weakness, as many people in the audience would say if I didn't point it out, is it's proved very difficult to use that theory and make testable predictions. And in my opinion, that certainly doesn't mean we should rule it out, but it has really put physics in a difficult place, I think it's fair to say now, because so many of the world's leading physicists are working on a theory that is seen as extremely promising, right, is based on quantum mechanics and relativity, which makes it rooted in two of the best tested experiments in science, but it lives most naturally at extremely high energies and is not readily testable in the laboratory. But I personally am optimistic that we're going to be making progress in that.
Thank you. Does this work? Okay. I was wondering if your book I read your book, I really enjoyed it. I was wondering if your book has one thesis or two theses. That is, there's one argument about the relationship between mathematics and physics up to the last 40 years.
Yeah.
But at the end of chapter 6, you seem to say what has happened in the last 40 years seems to be a bit different. It's not conventional science, insofar as it's working off of this Einstein-Dirac idea that you can be guided by pure mathematics apart from experiment. And it just seems to me that this thesis is a much stronger one and more questionable, partly for the things you were saying about string theory, that if you think about how Dirac tried to apply this theory, he saw the renormalization business, and he said, that can't be true because it's ugly. And maybe he's wrong, and that was the bad standard to use. And Einstein tried to use this not in order to form general relativity, but to go on this wild goose chase for a unified field theory. Why isn't it possible that this stronger thesis is wrong and sending people down the wrong road?
Could be. I doubt it, but it could be. One thing you always know about people who predict confidently about the future of science is they are always wrong, right? Right. What I am saying, right? And I believe it's a sensible strategy. It's certainly not mine. It's a strategy used by leading theoretical physicists working with mathematicians. Is that the advanced work they're doing in understanding the forces between fundamental particles, quantum field theory, and string theory, and the relationship between them, that they provide a wonderfully coherent framework that is fundamentally based, I say it again, but it's so important, on the special theory of relativity and quantum mechanics, which are extremely well grounded. And together, by jamming those things together, that takes you into these unbelievable mathematical territories. Now, if you ask me whether I know that is correct, I can't say that. It would just be dishonest of me. If I said that I believed it was heading in the right direction, I would say yes, and I'm simply according with the great majority of theoretical physicists. But remember George Bernard Shaw's statement: the minority is sometimes right, the majority is always wrong.
I have two questions, if you'll indulge me. You mentioned about crashing gluons together.
Sure.
How do you separate those from the proton? I assume you're using a proton. And what do you get when you crash two gluons together?
You get a lot of different things. The point is that, remember, that when we talk about the collisions in the Large Hadron Colliders, which what we're talking about now, you smash two protons together extremely high. It's a really very crude way of doing physics, but it's the best way of doing controlled experiments that we have. And in order to understand those collisions, the way you model them, so to speak, is by taking those two protons and recognizing that they're made of two different types of quark, up quark and down quark, with gluons binding them together. And when you look at the dynamics of those things, it's to do with quarks bashing into each other, gluons bashing into each other. Now, when you do that theoretical work, it enables you to actually calculate what's called the background, which is the stuff that the standard model of particle physics explains, right? Now, you can only do those calculations by using that theory, but no one actually sees one gluon, colliding head-on with another gluon. So it's something, so to speak, you're taking a very complicated thing, which is in my day, they used to call them dustbins because they're basically such complicated things, protons. You smash them together and you need a very complicated theoretical model to explain it. But ultimately, you're talking about fundamental particles colliding with each other.
Hi. If I really want to understand the universe, should I become a mathematician, a physicist, an astrophysicist? Does it not matter? Or should I become all three? Thank you.
Well, if you're smart enough to become all three, I'd do that, sir. A less frivolous reply is, remember that mathematicians are not, if you look at their job description, which I know is changing these days, but that's not their job. to understand the universe. Their job is to build on this, play this amazing game that they play, very serious game, right, of mathematics. It is the physicists who, but you might say arrogantly, want to try to understand the ordering of that universe. What we've been talking about tonight, or you've been hearing about, right, is that those two territories are increasingly overlapping, right? But it's the physicist's job, I contend, and I brook no argument about this, has to be about the universe.
Hi, I'm an algebraic geometer, actually, working with string theorists. And I have sort of one comment to make about what's going on sort of at the interface, which is it is very messy. There are lots and lots of ideas produced by string theorists that we algebraic geometers sort of interpret mathematically. We come up with ideas that when feed back to the string theorists, and most of it's garbage. I mean, it sort of eventually sort of synthesizes into something useful.
Yep.
I think that's an important point to make.
I agree with you. No, this is not a simple. It's not a simple linkage between and there are a lot of difficulties here. The mathematical, you sir are an algebraic geometer, are you trained in mathematics? I don't know whether you'd agree. It's pity the microphone's gone, but do say if you disagree. It seems to me that to some extent there are different cultures among mathematicians. A slower moving culture, very keen on knowing exactly what you're talking about, being very precise. Physicists tend to want to work at a much faster rate, so to speak. They're often happy to work with definitions that mathematicians are very fuzzy. So it's not always an easy collaboration. There's very few people who could do both of those things. Edward Witten is one of them. There's others as well. Nima Hamed, who's coming here next term, I know, who are very, very good at it. But I think you make a very good point that it's not a simple thing to go between them, and relatively few people could be adept at both. So I'm glad you made that point.
Going back to the premise of your book as far as numbers, when you look at the arrangement, the picture of the universe, what type of numbers are we looking at to explain the chaotic organization that we find?
Forgive me, I may be being obtuse. I don't quite get your question. May I trouble you to repeat it?
Well, when you look at the galaxies and supercluster of galaxies and walls and voids, it seems very chaotic. That what type of numbers you can explain that?
Well, yeah, I mean, this is the thing, you see, that's how I began my remarks here, that what is, to me, the most astonishing thing of all, and I'm quoting here from Einstein, which is a pretty good source, that in these extraordinary variety of phenomena, from your galaxies colliding, your black holes colliding, through to all the different varieties of Earth, are a relatively small number of simple laws, which Newton foresaw. Now, if you take those laws and you deploy them with their initial conditions, it gives us an amazing ability to understand the universe. And that, to me, is what makes physics fascinating, that it has brought the universe within the ambit of the human imagination. I think that is an incredible adventure to be fascinated by.
I've read your book, and it's really great, except for one thing. You left out half of the problem, and that was von Neumann and the fact that Hilbert space was the way to do quantum mechanics,
Yep. Mm-hmm.
and operator theory, and operator algebras, etc.
Yeah.
Now, I knew a lot of people that were working on group theory and infinite dimensional representation theory. And that was all going on after the Second World War. And that was essentially a brilliant piece of work. And it still is the major problem in quantum field theory. Mm-hmm. And I saw none of that in your book. Mm-hmm. Mm-hmm. And so it's an interesting collision between Dirac and von Neumann.
Yeah, no, it's always interested me that Dirac was never that interested in von Neumann's work. I stand by talking to Freeman Dyson, Karen Uhlenbeck, and goodness knows how many people, that by the standards of today, right, and the mid-19th century, the the relationship between pure mathematicians and physicists was a lot thinner than it is today. But you make a fair point that von Neumann and others were interested in this. But again, Niels Bohr wanted nothing to do with von Neumann, which is part of that divorce. But I think it's a fair point that perhaps von Neumann got cheated. I might say just one anecdote, if I may, very frivolously. Dirac, I've never saw any evidence that he actually talked physics with von Neumann, but he did go to the movies with him.
I have one question here, which was, what should we take away from the informality of the math in Einstein's miracle year papers?
So I didn't catch the last bit, I'm sorry.
Yeah, what should we take away from your kind of thesis about the informality of the math in Einstein's miracle year?
Okay, well, I would say that at that juncture in history, it really was possible to use, if you'll forgive me, basic mathematics to do great physics. Right? Today, there are very, very good physicists, let me be really clear, who do superb work without using advanced mathematics. What I've been talking about is a subset, so to speak, that are looking at fundamental physics, at the extremes of energy and size and what have you, right? And there, whether you like it or not, if you go deeply enough into whether you look at gluons or theories of gravity across the universe, you are driven into more advanced mathematics. So it is possible to do physics in the whole domain of this glorious subject, right? But if you go into the fundamentals deeply enough, it seems, as Dirac said in that thing that I quoted, you keep finding yourself at the frontiers. But if I might say, my friend Martin Rees often says this: if you're not strong mathematically, it's best to keep away from this field. You can still do good physics, right? But it's not going to be stuff that is about colliding gluons and theories of gravitation. But it's a perfectly fair point.
Although, as the director of graduate studies, I should say you shouldn't count yourself out. Right? It takes a long time to find out whether you have a knack for this stuff. So
it didn't take me long. It's tough.
Your mileage may vary. Yeah.
Now I'm being tactless. You're being the good teacher.
Yeah. But that's, in all seriousness, if you're considering studying this stuff, don't give up. Like in my experience, a lot of people who lacked confidence and really worked very hard, they got very far.
And it's worth just underlining that point, which is absolutely excellent point. If I had to pick something that really made me admire Einstein more, it was the determination that he had to overcome, because he wasn't a great mathematician like Hilbert, right? But he was absolutely determined to get to that goal, which he did. And that really was a Herculean task for him. And that illustrates your point in a sense. He wasn't somebody who'd be a star here at Harvard in your maths department, but he was determined somehow to get onto their territory. He brilliantly did it.
I don't know that there's a single theorem that Einstein ever proved, other than the Pythagorean theorem as a child.
Summation convention is the only thing I remember in mathematics. Yeah. But yeah.
That is all the questions we have time for tonight. I think we'll end there. One more round of applause.
Thank you very much. Thank you very much.
Thank you. It's a pleasure.
Thank you.